Good morning and welcome, everyone. Yesterday was such a great day of learning. We started with learning how to be more energy resilient with solar PV paired with batteries. We moved on to the wonderful world of carbon storing hemp building materials, and we ended the day by being reminded to think alternatively to convention and how to build innovation into our businesses every day. And as great as yesterday was, I'm even more excited about today's lineup, which in addition to this session speaker includes the well-known Martha Rose, who will be speaking about her process for building unvented roofs without using foam, and First Lamp, who will be taking us on a deep dive with their Green Building Slam project, the Ballard Passive House. Just a quick note for folks new to Remo, to better view the presentation, you can minimize your chat box, which is off to the right, by clicking the green arrow in the top right corner. You can also maximize any image on your screen by clicking on the 4 arrows in the top right corner. I would like to take a moment right now to honor the land that we currently occupy. We, on behalf of the Northwest Eco Building Guild, we acknowledge that we are all on the traditional land.
Hi, Helen. You're not sharing your screen. Oh, there we go.
Johnny's a little late to the game. Sorry about that. Can we switch to the... Sorry, technical difficulties here. Okay. Back up, rewind. On behalf of the Guild, I'd like to acknowledge that we're all on traditional land of the first people of this region. We honor with gratitude the land itself and the tribal people who have been faithful stewards of the land. Here in Seattle, where I am, it's the land of the Duwamish. Many of us are attending the summit from other parts of the region or even out of state. If you don't currently know whose traditional land you work and live, we encourage you to find out. We're going to post a link in the chat section that will help you find out that information. Thank you for taking a moment with us. We're here today because of our collected interest in sustainable building. For those of you who have been a part of the Guild for a while now, you know that our unofficial motto is pushing the envelope. And on a literal level, we're often talking about the physical envelope of a building. But one of the most impactful envelopes that we can push is about people, equity, social justice, climate justice. So as you attend the various sessions over the next couple of weeks, we invite you to keep this aspect of sustainability in mind, and we invite you to be a part of our journey in helping to bring light to this area of work that's so critical to building our brighter future for the 7th generation. We would also like to thank our sponsors for the event. John's sitting side by side. I keep looking over at him. We've got our sustaining sponsors, King County Green Tools, Dunn Lumber, and Farrow's Creative. We've also got our supporting sponsors, which there are so many to mention individually, but we couldn't do it without them. And finally, we've got our contributing sponsors as well. Please help us give them thanks with silent claps from wherever you are. Sponsor tables have been set throughout the event, so you'll see them off to the right-hand side of the floor. Be sure to stop by and see what they're all about. Before we introduce our speaker today, I'd like to give a little info about Remo. We're really excited about this platform and its user experience that we hope we will get from it. But when we get back to the floor view after the presentation's over, you can see in the picture what it looks like. You'll discover that it's easy to move from table to table, and it's fairly new software, so we're prepared to help you find your way around and get reoriented with it. Instead of pointing out bathrooms, we are going to point to the 4 corners of our floor plan where you can access additional help. Outlined in yellow in the upper left-hand corner of the floor screen are basic tips and support. Just past that is the little purple circle, which is where you can check to see if you're having microphone or camera issues. If you want help from us, you can go to the lower right corner help desk. Somebody will spot you over there and come help you. And if there's a real problem, you can go over to the lower left corner of the screen where you will get access to Remo support. And we've also got a little blow up there of our icons, and anyone with a star next to it is an event host. And you can also privately chat them by scrolling over and clicking on the little chat bubble icon, and that will send a message directly to them as well. Again, I'm being joined by John Harrison. He's going to help manage Q&A for us and any technical issues. So if anyone during the session has some technical issues they'd like assistance with, you can send John an individual chat. This course is AIA approved for 1 CEU. If you haven't picked up your reporting form, you can grab it from the chat box. John is going to place it in the general chat for everyone to pick up. So now on to our speaker. This morning we have Shimrit Finkel joining us virtually all the way from Israel, where I think it's about 6 p.m. there. She is a PhD biologist and CEO of her company. For those of you who caught our keynote session with Commissioner Franz, you'll remember how Commissioner Franz discussed the amount of marine land that the DNR is responsible for. And so for us here in the Pacific Northwest, even though we focus on buildings and on land, we recognize our effect on marine ecosystems. So I think this is going to be some fascinating information for all of us. Shimrit, I invite you to come up onto the stage, which you've already done, and I will close out. That's all right. I will close out and let you take it on.
Thank you, Helen and John, and thank you for having me here today. It's a real pleasure. It's a real honor, and I'm presenting from Israel. So for me, it's like 7 p.m. now, and you're just starting the day, which is awesome. So I hope that I'll give you some stuff to think about. I'm going to share screen, and I hope everything ticks. I think you can see my screen now. Feel free to pop up any questions in the Q&A if you have. And I'm not sure if we're gonna answer them immediately or if we're going to wait until the end. We'll see how it flows, but definitely put them out there. So as mentioned, I'm a marine biologist. That's me diving here in the slide. And I started off working on basically man-made structures and artificial reefs, and how can we better design man-made structures to mimic natural reef features. And I've kind of migrated from that and from my academic experience to coming up with an innovation that helps people like you that are designing and building our future, our coastlines, our communities. How can we do that in a way that also invites the ecosystem and takes that into consideration? And specifically, I'm targeting concrete, which is very vast. So I'll go diving into the presentation now. The first problem that's kind of the background for why I'm actually working on this is us, population growth. We're about taking ecosystems that used to be very much pristine. If it's the swamp area that used to be Manhattan and was completely transformed into an urban environment, or if it's other regions that had oyster reefs or clam beds, and are now active waterfronts or ports or whatnot. So that's kind of losing a lot of biodiversity. And at the moment, we're at about 50% of our population residing along coastlines. And you have to consider that the entire coastal belt is about 15% from our footprint. So imagine the stress on those fragile ecosystems. About 70% of our coastal structures are concrete based. And this is all of our seawalls and our pier piles and our wave breakers. A lot of coastal construction that is based on concrete, making concrete today the second most consumed material in our planet, second only to water. It's quite scary. And concrete has a huge carbon footprint. The concrete industry is responsible for about 8% of our carbon emissions today. And obviously, that's a problem that's also fueling another global problem of climate change. So because of excess CO2 in our atmosphere, we're seeing more storms coming in more frequently and more intensively, and we're seeing obviously the impacts of sea level rise that are going to threaten a lot of us. And it's not just about us and our communities, it's also about the coastal ecosystems. And the fact that we're basically paving our coastlines with man-made structures and defenses, and that's a global phenomena. So if you look at the globe, and this map is by the UN, all the lines in red are heavily altered shorelines, not pristine, beautiful coastlines. It's armored, it's urbanized, etc. And it's typically coupled with cities with over 1 million people in population. What's happening is that we're overtaking the natural seascapes. It can be coral reefs, it can be mangrove beds, it can be oyster reefs, it can be rocky reefs, which were actually the natural lines of defenses for our coastal systems. These are the natural breakwaters that we used to have, and we're losing them for concrete deserts. And instead of utilizing the way nature intended, we're building concrete deserts typically. And it's not even then that it's only the problem of not having the life develop, it's also the problem of having the population squeeze those ecosystems on one hand, so we can't really build much more into the ocean, or I hope we won't do a lot of building into the ocean on one hand. And on the other hand, with sea level rise, it means that the entire intertidal zone is now being basically compressed into a very narrow vertical belt, which really takes its toll on biodiversity and on productivity. And this concept of coastal squeeze, that's something I want you to keep in mind. And if you look at how we tackle this issue, I mean, there's several ways you can think about it. It's like an area of solutions where I would think that the best way would be just to let nature take its course and realign. If we can, we don't have to live that close to the ocean. We can step back a mile or two and just let erosion happen. But it's not always the case, and it's not always possible. And in those cases, we might need to consider some softer measures like living shorelines and like natural inspired solutions. But not always do we have kind of the horizontal space to think about these solutions. If we're in the city, we can't really imagine now that we're going to have, you know, a full intertidal zone in the middle of the city to function as a barrier. And that's where we kind of go hard, and we go with vertical concrete solutions. And that's where we come in. And we want to think about the way that we design those structures and think about the way that we utilize them. Can we actually utilize them for ecosystem services and for ecological purposes? It's kind of thinking about urban nature. Now, everybody knows, especially you guys, about urban nature in the city. How can we harness our roofs? How can we harness our parks for oxygen, for pollination zones, for various ecosystem services? But not a lot of us have stopped and thought about how can we utilize those vertical seawalls and pier piles and all of that surface area that's touching the water. At the moment, we're just letting, you know, whatever comes in. It's basically like having a park and not gardening it and just leaving it for weedy species. And that's exactly what happens. We're going to have weedy species, we're going to have invasive species, and we're going to have very little ecosystem services. So that's a concept that I want to be changed. Now, there's already a few very good examples for this kind of thinking, and I think you're sitting on top of one of those, the Seattle seawall. I think as an expert in this field of ecological engineering, it's one of the few and largest projects that have used these types of thinking. So it actually started with the scientific research in the University of Washington and a couple of colleagues, including Jason Toft, that were basically studying how can we design a seawall instead of having flat panels to have some features in the panels to accommodate for life. And they even took the extra step and they tested a different set of solutions. And after a successful study, it was actually scaled up, and it's one of the only examples when we have such a large scaling up of ecological engineering to the actual seawall in Seattle, and it's functioning. And in addition, they also thought about other ecosystem components like the salmon migration across the walls, and they put these light penetrating features on the boardwalk to allow for some natural light below the pier system. an area that actually caused a lot of stress for the fish and lost a lot of energy when they were trying to look for food. So this is a really good holistic thinking of different features. They also put some marine mattresses next to the seawall and habitat benches. The only thing they didn't touch is the actual material. So they still use standard concrete, and I'll touch that. So design features is a great component to start with, and you can definitely tailor the design features according to the needs of the local ecosystem and use local knowledge to optimize the solution. Another example comes from the UK. Here too, we're actually seeing a simple aspect of adding holes onto breakwaters. So it's pretty labor intensive. They actually went and they drilled holes of different diameters into rock, and they studied how that affects biodiversity. And they did see that it does function like a natural kind of water retaining features that you might find in rock pools. And they did study what is the diameter and what is the depth, and they even tried to go and design constructive solutions that really have those features in the form of this block, for example. Here too, it's a great step forward, but also there was only thinking about the design features. Here it was more in the macro scale. What I want you to think about is an extra layer. What about the material? Why concrete? And concrete, what does it do in the marine environment? So I can definitely tell you that concrete is not ideal for marine life for various reasons. First of all, it has a very harsh chemical composition. It has quite an alkaline feature, and the marine grade concrete is really full of different chemicals like corrosion inhibitors, freeze and thaw agents, workability agents. There's a real soup of chemicals into the marine grade concrete that's not healthy for marine life. So that's one aspect. The other one is the fact that typically we're casting very smooth surfaces. They don't allow really for the marine organisms to cling on. And we're typically, or engineers are typically doing things, you know, just one by one by one, the same feature, the same seawall. And when you have low structural diversity, you will also have low biological diversity. So that's another thing we want to change. And as I mentioned, if you're not taking care of your infrastructure onto those levels, we might have more invasive species. We might have more nuisance species. We will probably have a carpet of one or two key species that are very tolerant and will overtake the space and will create environmental problems. That will also drive a lot of regulatory pain. The permitting and the mitigation that's associated with structures is also a pain for the project. So these are all the things that we, and I'm saying we, this was our solution in-house, eConcrete. We wanted to tackle each of those, and we actually took a very, I think, unique approach as biologists that are working on concrete. We basically took a very biomimetic approach, and we really took it down and broke it down to the three problem areas that I mentioned: the material, the texture, and the three-dimensional design, and we're taking care of each of those systematically. Our first component is basically a bioenhancing admix component. It's like the salt and pepper for the concrete. It's a very low volume material. It's basically 10% of the cementitious materials in the concrete. And that's enough to neutralize the negative effects of the concrete and to facilitate a much healthier growth and healthier biodiversity. So that's one component, and basically at the moment we're supplying that out of Israel. In the future, we will have that manufactured in North America, in Asia, in Europe. At the moment, it's still transported, but it's a very small amount of the material. And by the way, it's over 90% byproducts of different industries, including the quarry industries, so it's very much sustainable. The other part of the technology is working on the texture. We want roughness. We are mimicking textures of oyster shells, mimicking textures of polyps. The idea is to create a habitat that larvae of oysters, of tube worms, of different organisms can actually adhere to. And it's even about micro level hydrodynamics. When you have a completely smooth surface, you have a very strong flow across the element and kind of a thick boundary layer. And that would not allow for the larvae to actually attach efficiently and to even encounter the surface. So when we're doing these modifications, we can allow for the little micro turbulence that will enable us to have a more efficient attachment. And finally, it's about the three-dimensional design. That's really where we're looking for nature. and natural features, and we integrate them into the element. If it's rock pool formations, if it's a hole for a certain fish that needs that diameter of a shelter, we will integrate that into the seawall, into the armor block or anything. Basically, any type of concrete solution, we can tweak it in order to have more life on it. And we will do so without compromising the strength or workability. That's very important. Otherwise, it's not going to be adopted by the industry. And this is kind of how it looks like. This is a panel after being submerged for a year in the Mediterranean. It's completely covered by oysters and tube worms and coralline algae. You hardly see the concrete anymore. And all this life is helping us serve multiple goals. A lot of them are in compliance with the UN Sustainable Development Goals that we very much care about, including the life below water, which is, by the way, the least treated goal of them all. But because I said we're working with byproducts, we're looking at sustainable cities, we have a lot of different themes that we think about when we deliver those solutions, those environmentally sensitive solutions, including, for example, outreach and education. And I'll explain. So what does all this life mean? First of all, it means an ecological uplift. When we are designing for the ecosystem, we can have more biological niches, better ecosystem services. For example, by having more filter feeders, we can have a better water quality. We can reduce the dominance of invasive species just by allowing for the natural species to colonize. And overall, a much more aesthetic and healthy community assemblage. And in addition, we can have carbon sink through photosynthesis and through the skeletons of organisms, for example. In addition, the beauty is that those organisms are actually protecting the concrete. It's kind of a shift in paradigm where until now, life on stuff on marine structures were looked at as biofouling as a bad thing. We want to get rid of that. We don't want to have life on the concrete because it might jeopardize it. Well, it's a wrong way of thinking about things, and there's multiple studies that show that this crust, especially when it's calcium carbonate based, like oysters and tube worms, it's actually protecting the concrete. It's reducing its sensitivity to corrosion, and it's reducing its sensitivity to just erosion. So we might be actually gaining a better longevity and reducing the maintenance over a long period of time, which will obviously also have some translation into monetary advantages. Looking at the Q&A, and I don't see anything. I'm moving forward. So carbon sink. Basically, when we have a whole lot of organisms that are growing on the concrete, especially ones that secrete calcium carbonate skeletons, we're basically generating an active carbon sink. What we're looking at is having activity of biocalcification, where these organisms are uptaking CO2 from the water and making it into calcium carbonate, therefore offsetting some of that huge carbon footprint of concrete. When it's on a square meter of concrete, it seems insignificant, but when you kind of span that and scale that across miles and miles of infrastructure, of ports, of marinas, of active waterfront, that's an asset. And on top of that, we can also have advantages of photosynthesis and overall get a much healthier system that's a lot less offensive to the environment. So we can look at different designs, and we look at really different applications that this can go into. It can be armor blocks, it can be seawalls, marine mattresses, new designs, retrofitting designs. It's really versatile. But I want to start and dive a little bit into the validation. So how did we actually start testing this? Well, it started around 2011 when we decided to go and look at concrete. We started looking at what materials can we put in the concrete and not decrease the strength of the concrete, but increase the settlement. So we did, I think we had like 15 different concrete mix designs in the beginning. And we went through an initial experimentation in the Mediterranean, which is kind of my backyard. And then once we saw like 5 concrete matrices that performed really well, we took and scaled that experiment. And we actually put, you can see these slabs, a part of them was textured and a part was smooth. And we had different concrete mix designs. And we had regular Portland cement-based concrete as well as the control. And we looked at all the combinations, and we did that from Key West, Savannah, Georgia, New York, and even up to the Great Lakes. We didn't have anything in the Northwest, but now we have some data from there. And we looked at recruitment in the field. Every 6 months we went and we dove and we explored what's growing, what species, how much cover we have. And we also looked at lab experiments where we actually took little tiny bits of concrete and we put larvae of different organisms and we checked how well they're doing in the very delicate phase of metamorphosis, which is kind of between having a polyp, like getting to the phase of a first polyp from the larvae. And the Portland is the control, that's the regular concrete, and the different mixed designs you see here are the different treatments we had. And we saw a huge increase. We saw an increase of between, for the best case, 5% settlement, and we had over 40% sometimes. So it was a real strong reaction, even just on the material level. And then when we went into kind of looking at it at the macro scale, we actually started developing different designs. For example, this tide pool. You can imagine rock pools that you have in a rocky beach. We wanted to mimic that and to integrate that. And here you can see the full design features. This is actually a precast element. And this is how life adheres to that. So we're really seeing at the micro level, even those crevices have a lot of organisms, and we're looking at a very high biodiversity that's really close to what we would typically found on the natural reef. So then we went into actual case studies, and we started working mainly in the US. We started around New York.
Shimrit.
Our first project was in Brooklyn Bridge Park, which really, yeah.
We've got a couple of questions here, if we can interrupt real quickly before you dive into the project.
Sure. Perfect. Let me go into those.
Yeah.
Yeah, I'm seeing. So the name of the concrete additive. Well, that's a part of our innovation. We call it Eco Powder. It's basically an in-house blend that has different materials that are byproducts mainly of the quarry industries. At the moment, as I mentioned, it's basically exported from Israel, and the exact chemical composition is our trade secret, but I'm happy to share some papers about that and the actual composition. It's non-hazardous, it's fine powders, it's reacting in a way that's similar to pozzolanic reactions within the concrete. And once we start working with it and the precaster starts working with it, initially we add it on top of the cement, and then we start reducing the Portland cement and actually replacing it with the Eco Powder. And by the way, I didn't mention, but we would prefer to work with slag cement as a basis. I think it's SEM3. So slag cement up to very high proportions, even 60–70% slag replacement. And on top of that, our Eco Powder would end up as a very good biological concrete. And you will also have a very low carbon footprint at the concrete level, even regardless of what I mentioned is offsetting. And regarding the settlement, for us, settlement is when a larvae of a marine organism shifts basically from being pelagic, like swimming larvae, into actually attaching to the substrate and starting to grow. In corals, it's called a planule, and when it swims, it has to find a surface in order to become the first polyp. We are now in the final stages of the Astm Standards, and we already have the compliance from the EU, the UK, and Australia. So I think it's in a matter of, I don't know, a month or two that we'll have the Astm specifications. And our mission is to have this as easy to use and as seamless to go through when you're doing a specification to the project. Cool, thanks. So I'm going back to the case studies. Brooklyn, this was a very post-industrial region with the old warehouses and crumbling piers. And we were very fortunate to actually work with the Department of Environmental Conservation. As a part of their permitting scheme, they wanted to see some demonstration with e-concrete. So we worked at the time, it was MVVA and the Brooklyn Bridge Park Corporation that were responsible for the project design. And we had basically two projects. One was ecological pier piles in Pier 6, and one was riprap enhancement with those tide pools at basically the Pier 4 beach. It's a constructed beach, and we added our tide pools in there. And what you can see here is with respect to the riprap, you can see a lot of riprap also in Washington, in California. It's pretty common to see that. And often people think that that's fine, it's a natural material. But that type of rock, which is typically a quarry rock, like a bluestone, it's not the natural rock from the marine environment. It's much denser, and it doesn't perform as a surrogate to a natural habitat. And therefore, our idea was, for example, to integrate those water retaining features, and really the inspiration was a tide pool from Laguna Beach, to integrate those precasts at the really mean high watermark, and to have those habitat features integrated into the constructed beach. And I can tell you that we did active monitoring for up to 2 years post-deployment. The pools are really high. They're very high in a place that the rock has no life, literally no life. And within the pools, we found up to 100% live cover of brown algae, green algae. We had a suit of copepods, amphipods. We saw some crabs that weren't spotted in the area. We saw fish larvae. So we really successfully pulled some of that ecosystem from the low watermark up to the beach. And what the beauty thing is that we actually got people to engage with them. So we've had educational tours from Brooklyn Bridge Park going and looking into this kind of urban nature, or almost like touch pools within the reprep. The other part that I mentioned was the pile encasement. And here it was basically just piles of wood that was deteriorating, and they needed to do a jacket. So the standard solution, you can see the control here, is a fiberglass form that is left in place. And as you see, after more than a year, it has almost nothing on it. We designed a surface that is much more textured. We designed it like a rope facade. And this is after the same amount of time. And we had basically double the biodiversity and double the species richness. We saw some mating crabs. And I think it was after 9 months, we even had recruitment of native oyster, which was really awesome. So, and these were really fine. I mean, these were changes that did not interfere with the engineering component of the park. It actually helped some components and did a lot of ecological uplift. Let's go into seawalls. That's a very, very typical feature of urban spaces, vertical seawalls. This is our solution of a seawall. You can see that it's very much textured, maybe a lot like some of the textures you can see around Seattle seawall, but here we also manipulated the concrete. And so we are seeing a very active process of what we call succession, which is how the marine life is adhering. For example, this was just a test done in Israel, but you can see when it goes into deployment. In this case, we put just kind of an add-on next to the seawall, but in the projects now we're working on in Florida, we're actually doing the seawall itself. And you can see over time how we're seeing a really, really nice development on the seawall. And we have studies, by the way, that I'm happy to share later, scientific publications with statistical analysis on the difference between the flat marina seawall that we actually scraped as a time zero comparison and our designed seawall. And you can see that the controls keeps on the same space. This type of analysis shows you what is the similarity between one sample point to the other. And in the control, they're all kind of scattered around the same spot. They're not really doing much. There's not much progression in the ecosystem. Whereas in our units, you can see that with time, there is a divergence and the ecosystem shifts to a place with much higher biodiversity. And that was typical not only for the invertebrates that really just cover the wall, but also to the mobile species, the fish, the crab. We found basically every hole had a fish, which was really awesome. So you can really design for that. Another project we've done was marine mattresses. This can be used for scar protection along the coastline, or even when you're placing, let's say, pipelines in the water, unfortunately, if you have to. Typically, they cover them with those concrete mats to prevent from erosion and damage. And then we designed one that can help also create an ecosystem. And here you can see two projects. One is in Miami, one is in Neptune, New Jersey. The typical mat will be featureless. It will just be bricks. And with our ones, you can see all these features. And we saw an amazing response, not only from the biology, we actually even saw a better response with the sediment deposition. Here, for example, you can see how resident fish have colonized the mat. And we did studies with the University of Nova. We had a couple of master's students that did this study. And they saw that we had significant more feeding on the mats that had the features than the mats that didn't have features on them. So it's really nice to see that in action. We also quantified, we took some bricks out and quantified the amount of calcium carbonate, for example. Here you can see in the deep regions, this is organic weight. So this is kind of how much soft or bodied organisms we had. And this is inorganic weight, how much calcium carbonate organisms we had. Control versus e-concrete in the deep, you can see it's like 3 times, 4 times as much. Definitely a good outcome from our end. I want to go into a case study that's closer to you and your hearts. This was a work that was done actually by Anchor QEA. It's their project. We were a minor component within that. But the project did look at a very deteriorated wall, and that really had erosion problems and stability problems. And the design feature was to integrate a new gravity wall system, basically a ready rock system. But we also integrated basically our technology onto the ready rock system, so that instead of just using Portland cement and their regular facade, we worked on their facade very, very lightly to increase life. And we also integrated those little mini mats. You saw the mattresses before. We wanted to integrate those into the design. And this is kind of how it looks after. We didn't treat the whole thing. We only treated the lower portion that's kind of really the active biological belt. And you can see we don't have a lot of data because it's less than, I think it's about a year now in the water. And with COVID, we didn't even have a chance to go. I didn't take these pictures, but we're being told that you can definitely see a clear enhancement. And we're also seeing some activity within those little water retaining features. What we did with the wall is to really work on the fine-tune texture. You can see it here with the scale. Instead of having those features that are more or less like a standard, rock, which is, again, not very rugged, we really elevated the roughness, and that contributes a lot to the capacity of the biology to develop. Here, I want to also mention that we did have the pleasure of getting some instructions from very wise people that are from the region, basically the First Nation people. They were an active part in the design process, saying what they think would work better than other features. And that was a beautiful process to see how the local community is engaging with the actual design. Next is a quick look onto Randall Island. And here we basically, this is a project by New York Parks. This is a situation where we had a historic wall here on Randall Island that needed some renovation. And the idea was to play with sea level rise projections. So we just designed a simple element. It's like a brick into the wall, but it also functions as a rock pool instead of just being a step in the wall. And Marcia Johnson, who did this design, actually did different elevations of the pools. And some of the pools are completely dry or freshwater at the moment. And some of them are down at the height of the water, more or less. So we're seeing really different communities develop. And you can see that there are marks of the elevation. At a certain stage, these pools will be completely submerged, and the ones that are dry will become an intertidal habitat. So it's a really cool project. And I really want to stress how beautiful it is when we work like scientists, or in this case, a commercial entity working with landscape architects, working with engineers to find more creative solutions that are more nature inclusive. Yeah, I'm seeing a question on the seawalls. So the seawall itself, we will design a seawall. So we will construct a full-on thun and groove seawall or gravity-based seawall and provide the entire seawall component. We do that with a local subcontractor that will get our system and our admix. But in certain cases, we can add on. We don't like to do an add-on. The engineers don't like to attach stuff to stuff, like concrete to concrete in harsh environments doesn't really work. But in certain cases, when we don't have a lot of choice, like in historic walls, sometimes we need to do some add-ons. But as an essence, we would prefer to work on the entire infrastructure from top to bottom, from the design phase up to the construction, and really do that from day one to design a seawall that's fully constructive and does include ecological features. I think that's one of the last examples that I'll show you, and I want to be sensitive with time and leave some more time for questions in the end. Armor blocks. I know that thankfully you guys don't know a lot about armor blocks, but when sea level rise comes and when you have more storms, like in New York, like in other regions in Europe, you need to use big blocks in order to prevent waves from deteriorating the beach, from destroying the streets, and sometimes you don't even have large enough rock, like riprap, to accommodate for that. And then a lot of the times you go to big concrete chunks. They're called antiferrous, there's Corlock, there's different designs and gizmos that are being used as armor blocks. And now I'm going to talk about armor blocks that also have a biological performance. So this is from a port in Israel. This is one of these armor blocks. They can be monsters. They can be the size of a room, and it's just a chunk of concrete. It doesn't have any features. It doesn't have, you can see here that you don't have, I'm sorry for the back noise. You don't have a lot of organisms. This is after a year in the water, or even after 2 years. Almost nothing grows on the regular concrete. And these are our solutions. So here we really manipulated the design. We did a lot of holes and crevices that were designed for the ecosystem. And we got a really amazing result. We have double the biodiversity, double the species richness, and a much more resemblance to natural reef communities. And this, again, we have a published scientific paper on this with some of the results. It's the same kind of analysis that I showed you before. This is the control antiferrous over time. There's not a lot happening. And these are the bioactive antiferrous that have features kind of in a completely different area. You can see the community differences. And when we looked at the composition with respect to invasive species, for example, on the Portland control, we only had 5 native and 10 invasive species, let's say, per square meter. On e-concrete, we had 21 natives. We still had invasive. So overall, we really reduced the dominance of the invasive species. We can't get rid of them. They're in the system. They're going to come. But if we make the substrate a bit more appealing to them, their dominance will drop and we'll have a lot more of the natives. And the same was for the fish. And really here, too, we designed it for gobies and blemmies, and every hole had a fish. And we also went back like 6 years later. We checked the concrete for strength, and everything works. Everything is solid. In this case of this armor block, we can even engage with active restoration tools. In this case, we worked with the Billion Oyster Project in New York. We prepared these discs that are handheld, and you can put them in an oyster hatchery and have them pre-seeded with oysters, and then they can be placed into the armor blocks. In this case, I'll just show you, I showed you some of the biological results earlier. These are our concrete mix designs, and this is the control. This was done by the Billion Oyster Project people, and you can see how much more colonization we had on the bioenhanced concrete. Last few slides I want to show you is Living Breakwaters project. I know you guys had the Resilient by Design competition in the West Coast. In the East Coast, we had the Rebuild by Design competition that came after Superstorm Sandy. We were fortunate enough to be a part of one of the teams that actually got the funding for a project, and we were a part of the Living Breakwaters project. It's basically a scheme, a necklace of breakwaters that's going to protect an area in Staten Island, New York, that got really eroded during the superstorm, including some loss of lives. And what we did, and this was really, we were a small part of a big team, but the team that was led by Scape Landscape Architects looked in a very full way on the project, to look at risk reduction, to look at the community, and to look at the ecology. And these 3 components have to work together. Now, obviously the risk reduction component is crucial. So we're looking at full structural models. This was in a fume in Canada to check for the performance of the breakwater in a model, in a scaled model, for like superstorm Sandy conditions with sea level rise scenarios. The unique thing is that we started to design features from a very macro level. Typical wave breakers are linear. And what we did was kind of integrate these reef streets that give it kind of the ecosystem like the crests that you have on a reef. So that was one layer of the complexity. And then within those reef streets, we put the design concrete that was really looking into different enhancement features, if it's for fish and for oysters. Another layer of the design was just the rock size. So we didn't just use one rock size as the engineers will typically use. We used different rock dimensions to create different niches. And on top of all that, the Billion Oyster Project tailored a huge oyster restoration program. So it's an amazing project that's hopefully going to go into construction within just a few months. And we really looked at the different ecosystem components at the leeward side, at the landward side, and took into consideration how can we maximize the habitat value and maximize risk reduction. Here, I also want to tell you that this was another case where we were fortunate enough to be able, as a team, to reduce the mitigation very heavily, because all of the envelope of the breakwater was considered on-site mitigation. So the mitigation penalties in New York State, they have mitigation banking option. The mitigation went down from 18 to 4 million. And we need to think about this globally, and I'm happy to say that we're starting to see more and more white papers about ecological engineering. They come in different forms and different names. Sometimes it's building with nature, nature-based solution. Not all of them are as fine-tuned on heavy-duty infrastructure like we're working on, but we're definitely seeing more and more research going into this. And one thing I want to flag out is what is called Wedge, Waterfront Edge Design Guidelines, made by the Metropolitan Waterfront Alliance in New York, which is basically like a lead system for coastal construction, where they have like a menu of solutions to come up with a more approachable, more accessible, more resilient waterfront, but also more ecological waterfront. I urge you to go check it out. They also have a credit system you can get certified by Wedge, and I think that's an awesome component to look into. I see one more question here. Biomimicry principles in e-concrete using marine concrete. So the biomimicry principles that I mentioned were, first of all, on the material level. So concrete is a very foreign material, and we looked at natural substrates, how they are structured in order to come up with a more benign material. So that's one complexity level at the material. The second level was at the roughness. So you will almost never find a smooth surface in nature, in marine nature. It will always be rugged. It will always have a lot of edges. We call it edge effect. So we mimic a lot of edge effect in our designs. And at the 3D level, instead of having those flat panels, we are adding those features kind of ins and outs in order to create more habitat and more complexity. And we're mimicking features like if it's mangrove roots or coral reefs or oyster beds, we can mimic that into the design features. Can your 60% slag cement be used on land construction projects? Yes, but I don't know if it's that often used on land. And by the way, the slag cement is not our innovation. That's something that you guys can use and has a lower carbon footprint. The reason they use it more in the water is because slag is protecting the rebar better than Portland cement. Slag cement is better performing in marine environment. It's less sensitive to attacks of chlorines from the water, and therefore engineers are happy to use it. It just happens to be, and that's one of the things that we've tested, that slag cement is better for marine life. So if you use slag cement, you're already in a better position, and our admix goes on top of that. So we add slag cement and we add our admix component. So I think I'm almost at really the last slide here, and that's kind of conclusions. We definitely see, and we see a lot of evidence coming up, even though the scale of them is not as massive, but we're getting there, that you can enhance the life on coastal and marine infrastructure, and you can do it in a way that's scalable, and you can do it in a way that's feasible, even in very urbanized environments. What we're seeing and what we're trying to stress is that we can actually harness biological processes like biocalcification, like biogenic growth, that will actually benefit the structure and the environment. So it's really working with nature, and for us. And finally, I think that one of the main issues for these types of projects to go into full scale is we need to work together. We need to work from the early planning stages, because once the specifications are out for a blank seawall, we can't do anything. So we have to work from the early design phases, and we have to collaborate between scientists, biologists, innovators, designers, policymakers. Everybody has to be on board, and then we'll have a much more holistic project. And we like to say it's kind of a win-win or a win-win-win, because we're seeing a lot more value from the structures that are going to be much more urban in the future. And I hope you guys in Washington State and in California and in North America will keep as much pristine coastlines as possible. And don't use concrete if you can, but if you have to use concrete, then use smart one.
Okay, Shimrit,
That's all.
we have one more question that's in right now, and I was going to ask if more questions come in. Can you read the questions out loud before?
Oh, I'm sorry. Yeah.
That's all right. Thank you.
So how much is the concrete you may customize to the different marine environments that exist, and how customized are they to specific regions of marine life? I'm considering to close the window. There's a lot of noise outside. Never mind. Well, the concrete, we have at the moment two main mix designs. One is for kind of temperate environment, cold water, and one for tropical environments. From our studies, that was sufficient. And with respect to terrestrial, I didn't talk about it. Maybe you saw a tiny slide on it in the presentation. We do have like a facade, like a green wall. It's basically a cladding system with our concrete that has a different mix design that's better suited for lichens and mosses and climbing vegetation. So that's kind of our third one. And with respect to the marine life, we do see some kind of general guidelines. So I mentioned having a rough surface and having a lot of different features will always enhance more marine life. But when you want to really dig into the local ecosystem needs, what we will typically do is go ahead and do a desktop study, or if we're lucky, go dive and see what are the problems in the ecosystem, what are we missing. We do sometimes research, historic research, like in New York, the oyster reefs used to be huge in Staten Island region, and they were functionally extinct. So when we built that ecosystem on the breakwaters, in the beginning, the local policymakers were saying, yes, but this is soft bottom sediments, and you're going to transform it into hard substrate now. And then we had to go back and show them, and their historic maps, that historically it actually had hard structures by nature. So we can tailor that into the design. I have another question. Are there studies that you know that you can point us to talk more about how marine concrete and its toxins affect marine life? So there's a few studies on that. I can kind of direct you. There's a group in the UK. The researcher is called Richard Coombs, and it's Exeter University. They actually have a website called something called Bioprotection. You can look into that. And they did some work on heavy metals that are leaching from concrete. Now, it's not like there's a halo of death around concrete structures, but you do see a low biodiversity, and you do see the effect on the marine life directly on the structure. And that could obviously have those implications on the rest of the ecosystem. So there's not a whole lot of science there, but there's definitely some studies that talk about what is leaching out of concrete, and some studies on basically the chemical traits of the concrete. And if you dive into that, you will see that there's very heavy chemistry there, especially in constructed, marine constructed infrastructure. Any other questions? And these are great questions. I really appreciate it. And yeah, okay. In building construction, we build a lot of flat concrete wall surfaces. Are there studies or examples of building complexity into those concrete surfaces as an advantage? I don't know of a whole lot of studies on that. I know that when you're basically looking into integrating green walls into structures, obviously you are going to create a whole ecosystem on that wall, and you are going to need to take care of, you know, attachment points and ways for the life to thrive. I don't know too much on that, but I can tell you that from our observation, and we're going to launch kind of a line of activity on retaining walls and noise kind of reducing walls around roads. I look at it all the time. I look at concrete all the time, and I see that once it gets old, and once it gets a bit eroded and not as smooth, you will start having much more features. Think about when do you start having that look of an old English wall? Not on fresh concrete, not on 10 years old concrete. you have to wait a lot of years until you kind of lose that edge of having a flat, very solid concrete. Only when it ages, that's where you start to have a natural recruitment of mosses, for example, and lichens. So I imagine that if you had features that would retain some humidity, it might be better, even if you don't have the mix design. But mind you, if the concrete will be very alkaline, even if you have water retaining on it, mosses and lichens will not grow, because that will be a real problem for them to cope with. Especially at the surface, the chemical composition of the concrete would adhere much to the surface. But yeah, sorry, I don't have a smart solution more than that. Happy to. And by the way, feel free to reach out. I had my email there earlier. I'm happy to write it in the chat in case you want to reach out later with some questions. And I'm happy also to share some of these publications and case studies, and share any other information. And I'm also happy to stick around at the tables and answer some more questions. I think I see another one coming. Just a sec. Okay, awesome, thanks. Yay. Can you talk about the carbon intensity versus regular concrete? Yeah, so regular concrete has a couple of problems. First of all, the clinker from which you make the Portland cement is very carbon intensive, both in the production process of the clinker, so you have to invest a lot of energy on producing the clinker from the raw material, and you also have to cook it, so you have to invest a lot of energy into that. And also in the process, there's a lot of CO2 being emitted. So I won't go into the numbers, and I didn't really go into a whole lot of life cycle analysis. We still need to do that. But what we do is reduce the amount of Portland cement in the mix with first of all, with slag that has a zero carbon footprint, because slag is a byproduct of the steel industry. It's still considered as a neutral from carbon footprint. So if we do a lot of slag replacement, and I mentioned that our admix, which is only 10%, but still that one is almost carbon neutral. So when you compare concrete to concrete, we can have quite a nice reduction. And we're now looking into collaborating with some other innovations that, there's like Carbon Cure, there's Lydia Tech, there's a bunch of innovation around injecting CO2 into concrete and curing in concrete. I believe that we could collaborate and we can put like innovation one top of the other. I have a question, seconding Helen's question. Our local carbon leadership forum and I are working on this a lot. What are the best solutions? Well, I mentioned some of the solutions on the carbon level are emerging. I can give a few names. I haven't checked. I haven't collaborated with them yet, but I know of Carbon Cure that are injecting CO2 into concrete. I know of Solidia Tech that are curing concrete in CO2. And there's Calera, I think, which comes from the West Coast, if I'm not mistaken. They're kind of using calcium carbonate to come up with a cementitious material. So these are a few of the innovations around that space. But I know the whole industry is now looking for alternatives to Portland cement. And I'm also even just working on recycled concrete and recycled sand and recycled aggregate. That is very interesting. The problem is, at least in the marine construction, that's not in compliance with the standards. So for example, what we'd love to work with recycled material inside the concrete, the engineer would not sign off of that because the lifespan of the project, of the structures, is typically between 30 to 50 to even over 100 years design life. And for that, they won't sign off on recycled material. There's still an industry gap here, I think. Very cool. Excellent questions. Excellent crowd.
All right. Thank you so much, Shimrit. I'm going to release everyone to do networking at the tables, so feel free to head to yours. And anyone that wants to continue the conversation further can join Shimrit at her table. Thank you.
Thanks. Thank you all.